Hello students, my name is Shayan Mitra, faculty member of Department of Electronics and Communication Engineering of Greater Kolkata College of Engineering and Management. Today our topic is about the introduction to system. The subject name is signal and system. So let's start with the lecture. This is the signal system subject, and this is the lecture number 6. Up to this lecture, up to the lecture 5, we have discussed different kind of signals, different kind of operation that could be act upon on different kind of system, different kind of signals. We have realized what is the basic properties of a system, what is the LTI system, why it is has been named as LTI, and we have started with the basic properties of system, in which we have only discussed the linearity property. We have completed the how the linearity property works in case of a system, and from this lecture we are going to discuss about the other remaining system properties that is important for our it is important for the relation of a system, or relation of a system, and the significance and the operations of a system in which or by which we can implement different kind of application we can apply different kind of application in a system. So let's start with the lecture number 6, where we are going to start with the system, or how the time invariant shift invariance of a system really means, and we will go on with the different kind of system properties. So as we can see that in this slide, basically the definition of time invariant or shift invariance of a system has been written here. And conceptually a system is time invariant if the behavior and characteristics of the system are fixed over time. It means with the flow of time, the characteristics of this system will be unchanged. That's the basic definition of a time invariant or shift invariance of a system. Now, for example, the RC circuit is time invariant if the resistance and the capacitance values R and C are constant over time. But as we have already know that with time, the resistance and the value of the resistance and the value of the capacitance changed with constant over time. So it will not be constant over time. So if the value of different kind of variables of a system is not if unchanged over time, it could be said as a time invariant shift invariance of a system. And specifically a system is time invariant if time shift in the input signal result in an identical time shift in the output signal. That's the important point. Now this is important feature of a time invariance shift invariance of a system, that if yn is the output of a discrete time invariant system, when xn is the input, then yn minus 0 is the output when x function of nn minus 0. It means if the input signal will go through a time shift of n, it could be any value, the output of that system will also go through the same kind of time shift. So that is the basic definition, the feature of a time invariant or shift invariance of a system, where the system it's that kind of a system where with the variance of the time, if the input signal varied by 2 discrete point or 3 discrete point, the same way the output signal will also be varied with that same amount of variance. That's why it has been known as shift invariance or time invariant. It means any kind of change in the signal will, the same kind of change will occur in the output signal. Now consider this system where yt is equal to x2t. where what you have done is a time scaling process has been put through that signal, that is y function of t is a time compressed by a factor of 2, and because of the time compressed, the frequency of the signal will increase and the graphic function of that signal will be compressed. Now any time shift in the input will also be compressed by a factor of 2, and it is for the reason that the system is not time invariant. Now if you consider this system has been yt is equal to x function of 2t. Now how it works? Now if you take a closer look here, that this is the input signal and this is the output signal. Now what the function is? Now this is x2t. Now the output signal, the y function of t is equal to x function of 2t. It means if we scaled down this function, we will get this function or this signal as an output. Now if we have to scale down, this is the function where the function is known as x function of t, where the value of function x function of t is equal to 1 when the value of t is in between -2 to 2. Now if we provide this signal with time scaling, what will happen? The signal that we get at the output part is this. It's a time scale signal of this, because the system has been defined with this mathematical representation where the time scaling of x function of t is the output of that system. So this is the output of this signal. Now what we will do, this is the input signal that we have already known. Now what will happen here, that this is the function. Now what we will have to do, that any time shift in the input will also be compressed by a factor of 2. Now what is this? This is the signal. Now what we have done here, we have already understood what is time scaling and time shifting are. Now in this lecture we are going to apply this all this feature that have the operations of signal that we have already learned in the system part. Now this is the input signal. Now here we have time shift this specific input signal. How we have done it? We have just enter a value -2 in that signal. Now as we have entered -2, what will happen? The signal will the feature of the signal, the characteristics of that signal will not change, but as we have put -2, the signal will be delayed, or there will be a right shift of that signal. Now after the right shift of this signal, what will happen? The signal will start from 0 to 4. It means the signal will provide you the same value, but the condition here has changed. In the first case, the signal will be 1, the x function of t is equal to 1 when the value of t will be if the value of t will is between -2 to 2. Now after the time shifting, the signal that we have what you have get is that x function of t will be 1 if the value of t is between 0 to 4. That's the basic, that's the change that we have got after the time shifting. Now after the right shift of this specific signal, we got this value is that x function of t is equal to 1 if the value of t is between 0 to 4. So the few feature of the signal has been changed. Now after this thing, this signal will be provided into the input of a system. Now the system will be same. The system, what is the system? Now this is the input signal. Now system is what the system has provided us. The system has provided us output signal, which is nothing but a time scale signal of the input signal by a factor 2. Now it means the input signal will be scaled by a factor of 2. So this is the input signal now after the time shifting of -2. Now we have fed it into the input of the system. Now the output of the system will be provided here after the time scaling. What will happen? This is the output signal. It means this output signal that we have already gained here, it is different. It is compressed by 2. This signal also compressed by 2, but the signal that you have provided with is this. The signal hasn't shifted. The signal hasn't shifted in this way. So the system is not a time invariant system. Yes. Because if this is the signal and this is the signal, now if -2 has been provided and the time shifting of the signal has happened, this is the input signal. If the system is a time invariant system, then this input signal will be, after the time shifting of -2, the signal should be look like this, because of the right side shift of the signal. After the time shifting by -2, this output signal should look like this. After what we got from the output of the system, but as we have provided the input signal in this way to the system, we get this kind of output. Both are different, so that's why it's not time invariant system. It means so what you have already discussed here, that this is the input signal and this is the output signal. So what you have already discussed here, that this is the input signal of this function of the system and this is the output signal. Now if we have to shift this signal by -2, the shift of this signal will also be the same, and that will be this. But in case of this system, the input signal is this and the output of this input signal is this, and that is different from the desired output of the system if the system needs to be a linear time invariant or linear shift invariant system. So this is the basic of the linear time invariant system. So let's go to the next slide. Okay, so this is another example. Consider the continuous time system defined by y function of t is equal to sine x function of t. To check that this system is time invariant, we must determine whether the time invariance property holds for any input or any time shift t0. Thus, let x1 function of t be an arbitrary input to the system, and let y1 function of t is equal to sine x1 function of t. Simple form is there to be considered output. Then consider a second input obtained by shifting x1 function of t in time. So we will just shift this x1 function of t by -t0. Now if this signal has been shifted by -20, the output corresponding to the input should also be the same. So what will happen here? Now the output corresponding to this input is y2 function of t is equal to sine x2 function of t is equal to sine x1. We just put the value of x2t here, and this is the sine function. Now this y2t will be this. Now similarly from equation 1.115 means this, from this function we will put the same thing. We just put the -t0 value here. We will also put this value here. So comparing these two equations, we see that this, and therefore this system is time invariant. Basically this is the system. This is the function or mathematical representation of the system. The system has been represented by this function. Okay, so this is the output and this is the input function. Now what we will do, we will change the input. Now what is the input? The input is this is the input, this is the input function. Now what we have done, we have just provided it with a -t0. It means we have provided with a right hand shift or right shift of the signal, and the value will be t0, -t0. We just put that value in the input signal. So this is the new input signal. So with this new input signal, this will be the new output signal. Because of this new input signal, this will be the new output signal. Sorry. Okay, so this is the new output signal. Now, and this is the input signal that we have already discussed here. So this is the new output signal, this is the new input signal. So now if we just put the value y1 t minus t0, okay, in this signal, okay, this is the first one, this is the This is the first signal that we have provided with. So as we have provided with the time shift of minus t0 in the y1 t, so this value will also be provided with sin x1 t minus t0. So after, if we change the input signal with this minus t0, the value is same, and also if we put the y1 minus t0, the output will also be the same. So in both the cases, the input signal is same and also the output signal is also same. So if we vary the input signal, the output signal is also varied with same accordance with the input signal. So that's why both this signal or this system, basically this system which has been represented with this mathematical representation, it will be a time invariant system. So let's go to the next slide. So this one is the another basic system properties, which is known as stability. So let's discuss this phenomena here. Stability is another important system property. Informally, a stable system is one in which small inputs lead to responses that do not diverge. It means with a small input, the output will not the output will not vary so much. If we suspect that a system is unstable, then a useful strategy to verify this is to look for a specific bounded input that leads to an unbounded output. A system is said to be a bounded input and bounded output stable if every bounded input results in a bounded output. So let's go to the next slide. Now example of a stable system. Example of a stable function here is the system represented by y function of t is equal to ax function of t is unstable. How? If a is greater than 1. Reason, let us assume x function of t is equal to ut. Then at every instant, then at every instant u t will keep on multiplying with a, hence it will not be bounded. Now suppose this is y function of n and the value is from minus n, from minus infinity to n. The uk is equal to n plus 1 u function of n. un is a step function, so the value of step function will be 1 in each case. Now y is equal to 0, the value of this is 1 because n is equal to 0, the value will be 1. Now y1, when n is equal to 1, it will mean it is 2, so this value will be 2. So as we increase the value of n, the output of this signal will also be increased. It means that if we provide it with a bounded input, the output will not be bounded because it will increase and so on. It will just goes on and on. It grows without a bound. So this is not a bounded stable function. So let's go to the, so this is the, it means a stable function will always be expressed as a way where the function or the system will, if we have to understand the system is stable or not, it means with a small change of response of the inputs, with a small change in the input signal, if the response of the output signal is diversified or diverged with a huge value, then it is an unstable signal. But with a small change of the input signal, the value of the output signal will not change so much, or it will more or less constant or similar to the previous value, then that system can be considered as a stable function, basically a stable signal, stable system, sorry. So let's go to the next slide. Causality, how it has been described here. A system is causal if the output, the system is a causal system if the output at any time depends only on values of the input at the present time and in the past. Such a system is often referred to as being non-anticipative. The system output does not anticipate future values of the input. The RC circuit is a causal function. Now the causality or the causal means it works at the cause and effect value. It means if there is a reason, then there will be an effect. Now as we can understood or we can assume that the value of the value of a system or the value of the input signal at the future is indefinite. It can't be predicted, it can't be measured, but the value of the value of the, suppose value of the input signal at present time can be predicted, can be anticipated, but the value of the future values can't be anticipated. That's why it's a non-anticipative system. Causality of causality means a non-anticipative feature or nature of the system. The output of this kind of in case of causality, the output will only depend on past values and the present value. It means the values that has already been considered or mentioned or calculated, on those respect the value of that input signal can be considered in case of causality. But the value which need to be anticipation, need to be imagined, you have to consider. You can't mention the values of the input signal future is not mentioned or considered. It is need to be predicted according to the input signal, according to the feature of the nature of the input signal. We have to predict the future value of the output signal or the input signal. According to the input signal, to predict the future value of the output signal. So, but in case of causality, as the names refer here, that it depends. It's a causal. Causal means the cause and effect. From that word, from those words, the causality has been coined. So, that's why it is known as non-anticipative. You can't anticipate the value of a function or of the output signal depending on the input signal in case of causality. So, a causal function represent a function where the value of the output signal only depends on past and the present value, not on the future value, because it can't be predicted. It only depends upon the values that has already been considered or mentioned or calculated. We can't imagine or we can't put any imaginative value or predicted value in case of causal function. So here is a mathematical representation of a causal function. Y function of n is equal to summation of minus infinity to n, and that is k. And second example is a delay. So this is the causal. And in case of this is the causal, in case of non-causal function, now it's a vice versa. If you have to consider non-causal function, it means it will anticipative function. It can the function in case of non-causal function, we will consider the future value of a function or the input signal. According to the input signal, we can predict the future value of output signal in case of non-causal function. So these are the example of non-causal signals where the y function of n is equal to xn minus x minus n. N plus 1 is the input value of the future. This is the present value, and this is the next value. This is the next value. Sorry, this is the next value. So this is the example of non-causal function. In the next lecture, we will cover the whole properties of this, where we will cover the invertibility without the function of without memory and with memory. All these kind of things will be covered, and we will end that module 1. Okay. So thank you, student. Thank you. Good night.